Every single day, 15,000 people walk into the Empire State Building, ride its elevators, use its bathrooms, fill their coffee cups, and never once ask the question that should stop them cold. Where is that water coming from? You are standing on a 102nd floor of a building that rises 1,454 feet above the streets of Manhattan. The nearest reservoir is miles away and hundreds of feet below you. And yet water flows out of that tap like it's nothing. Like gravity doesn't exist. Like physics simply decided to make an exception for New York City. It didn't. Someone solved this. Someone engineered a solution so elegant, so quietly brilliant that it has been hiding inside the walls of the most famous building in the world for nearly 100 years, and almost nobody knows it's there. Stay until the end, because the sewage answer is even better than the water answer. And if you're new here, subscribe now. We find the questions nobody thought to ask. To understand how water reaches the 102nd floor, we have to go back to 1929 to a Midtown Manhattan lot and to the single most audacious construction bet in American history. It's 1929, the economy is about to collapse, but nobody knows that yet. What everybody knows is that New York City is in the middle of a skyscraper arms race, and the prize isn't money, it's the sky itself. The Chrysler Building is going up on 42nd Street. 40 Wall Street is climbing fast. Every developer in Manhattan is watching every other developer, measuring, calculating, trying to figure out how to build higher, faster, and more permanently than everyone else. Into this war walks John Jacob Raskob, former General Motors executive, financial architect, a man who understands leverage in ways most people only dream about. He buys the site of the old Waldorf Astoria Hotel on 34th Street and 5th Avenue, assembles a development group, and announces a building of 1,050 feet. Then the Chrysler Building secretly adds a spire and hits 1,046 feet. Raskob finds out, he adds 16 floors to his plans overnight. Then he adds a mooring mast for dirigibles on top of that. Part vanity, part genuine belief that the future of air travel was blimps docking at skyscrapers. The final height, 1,454 feet. The name, the Empire State Building. The architect is William Lamb of Shreve, Lamb & Harmon. His design brief from Raskob is one of the most famous instructions in architecture history. Raskob holds up a thick pencil and asks, how high can you make it so that it won't fall down? Construction begins on March 17, 1930. What follows is one of the most violent and precise construction operations ever attempted. At peak, 3,400 workers are on site every single day, 7 million man-hours total. The building rises at a rate of 4.5 floors per week, a pace so fast that workers on the upper floors are eating lunch before the steel below them has fully cooled from the foundry. The steel comes from Pittsburgh and Phoenixville, Pennsylvania. It arrives in Manhattan still warm. A relay system of rail cars, flatbeds, and derricks moves the beams from the rail yards to the site to the air in a continuous chain, designed so that no piece of steel sits on the ground for more than 24 hours. Riveting gangs work in teams of 4. One man heats the rivet in a portable forge until it glows orange. He tosses it, sometimes 30, sometimes 50 feet through the open air, to the catcher, who grabs it with a metal bucket. The bucket holds it in place. The riveter drives it home with a pneumatic hammer. Boom. Next one, they do this thousands of times per day. In the rain, in the cold, on open steel beams with nothing below them but Manhattan. The limestone cladding comes from Indiana, the same limestone used in the Pentagon and the National Cathedral. It covers 730,000 square feet of exterior surface. It was hand cut, hand fitted, and set by masons who had been brought in because they were simply the best in the world at what they did. The building is completed in 410 days. It opens on May 1st, 1931. It is the tallest structure on Earth, a title it will hold for 41 years. But here is what the opening day photographs don't show you. Behind those limestone walls, inside that steel skeleton, someone has solved one of the most brutally difficult engineering problems in the history of urban construction. How do you get water to the top of a 102-story building? The answer is not a pump. Well, it starts with a pump, but if you think a single pump pushing water from street level to the 102nd floor is the solution, you have never met the physics of fluid pressure. Water pressure is measured in PSI, pounds per square inch. The water main in the street below the Empire State Building delivers water at roughly 40 to 80 psi. That is enough pressure to push water maybe 6 or 7 floors up a pipe before the pressure becomes insufficient to continue rising. The Empire State Building has 102 floors. A single pump powerful enough to push water all the way to the top would create such extreme pressure in the lower floors that every pipe in the building would require walls thick enough to contain it, adding enormous weight, enormous cost, and creating a system so rigid that any failure at any point would be catastrophic. The engineers at Shreve, Lamb & Harmon don't try to brute force the problem, they think in zones. The building is divided into vertical pressure zones. Each zone is roughly 20 to 30 floors. At the top of each zone sits a tank, a rooftop gravity tank made of wood and steel holding tens of thousands of gallons of water. These tanks are the solution. These tanks are the secret. Here's how it works. Electric pumps at the basement level push water upward, not to the top floor but to the tank at the top of the first zone. From that tank, gravity does the work. Water flows downward through the distribution system to every faucet, toilet, and pipe in that zone at exactly the pressure the height difference creates, controlled, consistent, sustainable. When the tank in zone 1 is full, the pump kicks on again and pushes water to the tank at the top of zone 2. From there, gravity serves zone 2, and so on, up the building, zone by zone, tank by tank, all the way to the upper floors. At the very top of the Empire State Building, there are rooftop tanks that most visitors never see. They sit just above the mechanical floors, wrapped in their wooden stave construction, holding water that has been lifted there in stages by a series of pumps working in relay. From those tanks, gravity delivers water to the highest occupied floors. The pressure at any given faucet in the building is determined not by a pump running at that moment, but by the height of the water in the tank above it. This means the pressure is smooth, consistent, and completely independent of whether any pump is currently operating. If the power goes out, the tank still holds tens of thousands of gallons. The building still has water pressure for hours. This system predates the Empire State Building. New York City developed the rooftop tank standard in the 1800s when cast iron pipes couldn't handle the pressure a direct pump would require. But the Empire State Building scales this principle to a height and complexity that had never been attempted before. The vertical plumbing infrastructure inside this building is essentially a series of miniature municipal water systems stacked on top of each other, each one complete and self-contained. The pipes themselves are a story. During original construction, the plumbing system required over 70 miles of pipe. 70 miles. Inside one building, that pipe network carries cold water, hot water, and fire suppression water to every floor, in separate dedicated lines each size to handle peak demand without pressure loss. The hot water system adds another layer of complexity. Cold water tanks are relatively straightforward. Fill them, let gravity work. Hot water requires a heating system on each zone, because you cannot heat water at the basement level and pump it 1,000 feet up without losing all the heat through the pipe walls before it arrives. So the hot water heating infrastructure is distributed vertically throughout the building. Multiple boiler systems, multiple zones, each one serving its own section of floors. The water towers on the roof are made of wood, specifically clear vertical grain Douglas fir or cedar, bent into staves and bound with steel hoops, exactly like a barrel. This isn't nostalgia. Wood is a better material for this application than steel or concrete. It's lighter, which matters on a roof. It's naturally insulating, which keeps the water from freezing in winter or warming too much in summer. And it self-seals as the wood swells when wet, creating a tighter joint than any mechanical fitting. There are over 10,000 of these wooden water towers on rooftops across New York City. The Empire State Building has relied on this technology since 1931. The same basic design, the same basic principle, still working. Now, the sewage. This is the part of the question that nobody asks in polite company, but it is genuinely fascinating. And the engineering answer is in some ways more elegant than the water delivery system. When someone on the 102nd floor flushes a toilet, what happens? The instinctive answer is, it falls. Gravity down the pipe. Simple. The real answer is yes, but if you let 15,000 people's wastewater fall uncontrolled through 100 stories of pipe, you don't get drainage, you get a disaster. The problem is something called hydraulic jump combined with pressure transients. When water falls rapidly through a tall vertical pipe, it accelerates. As it accelerates, it creates a partial vacuum above it and a pressure wave below it. In a tall building with dozens of floors draining into the same stack, these pressure fluctuations propagate up and down the pipe, slamming into trapped seals, forcing sewer gas back into bathrooms, and in extreme cases creating enough negative pressure to literally suck water out of floor drains and create a direct open path between the sewer system and the occupied building. The solution is called the drainage stack system, combined with vent stacks. Every drain in the building connects to a vent pipe that runs parallel to the drainage stack and opens to the outside air. This vent pipe does one critical job. It keeps the air pressure inside the drainage system equalized with atmospheric pressure. When water falls through the drain stack and tries to pull a vacuum above it, the vent pipe immediately replaces that air. No vacuum forms, no trap seals get broken, no sewer gas enters the building. But in a building of 102 floors, even a properly vented stack has a terminal velocity problem. Water falling freely through a vertical pipe accelerates under gravity until it reaches terminal velocity, roughly 15 to 20 feet per second in a standard 4-inch pipe. At that speed, when the water hits the first horizontal turn at the base of the stack and has to change direction, the impact forces are enormous. Enough to crack pipes, enough to destroy joints. The Empire State Building's drainage system manages this with offset stacks, deliberate horizontal offsets built into the vertical drainage lines every certain number of floors. These offsets act as energy brakes, slowing the falling water and dissipating the velocity before it can build to dangerous levels. The water hits the offset, slows, and then continues downward at a controlled speed. At the base of the building, the main drainage lines run horizontally through the basement and sub-basement levels, carrying everything out to the city's combined sewer system beneath 34th Street. The building connects to the municipal sewer at multiple points, sized to handle peak discharge loads, which in a building of this occupancy can be substantial during morning and midday rush periods when thousands of people are using facilities simultaneously. The vertical distance that sewage travels from the 102nd floor to the street, over 1,200 feet, is actually an advantage. Unlike water delivery, which fights gravity, drainage harnesses it completely. The building essentially uses its own height as the driving force for waste removal. No pumps required for the main drainage. Gravity does it all, managed and controlled, from the 102nd floor to the Manhattan sewer grid. There are basement ejector pumps for below-grade fixtures where the drainage can't reach the sewer by gravity alone. But for everything at street level and above, which is the overwhelming majority of the building, the system is entirely passive. The Empire State Building has been renovated significantly since 1931. The 2009 to 2014 energy retrofit was one of the largest commercial building retrofits ever undertaken. New windows, new insulation, rebuilt mechanical systems. The plumbing infrastructure has been updated in phases. Modern pipe materials replacing the original iron in many sections, new pump technology improving efficiency, updated fixtures reducing water consumption by millions of gallons per year. But the fundamental architecture of the system, zone by zone, tank by tank, gravity delivering where pumps cannot, remains exactly what it was in 1931. The wooden water towers still sit on the roof. The vent stacks still equalize pressure across 102 floors. The drainage offsets still bleed velocity out of falling wastewater because the engineers who built this building in 410 days under impossible pressure for a man who held up a pencil and asked how high can you go, those engineers solved the problem correctly the first time. 630 feet of steel reach into the Missouri sky. 1,454 feet of limestone and steel reach into the Manhattan sky. Different structures, different eras. Same question underneath all of it. How do you build something that lasts? You solve the boring problems brilliantly. The water, the drainage, the pressure, the things nobody photographs and nobody tours and nobody talks about at dinner. The Empire State Building has delivered water to the 102nd floor every single day for 93 years. The question was never whether it could be done. The question was always whether anyone was willing to think hard enough to figure out how. Subscribe. The next impossible question is already waiting.